So let's take a look at double integrals in polar coordinates. So let's say we're trying to find the double integral of some multivariable function f of x, y described by region R in polar form, and we're trying to evaluate the double integral in polar form. Let's say that the angle theta is in between alpha and beta, so two different angles, and then the radius is in between A and B. So using three formulas here, x equals r cosine theta, y equals r sine of theta, and then x squared plus y squared equals r squared. The formula to turn this double integral into another double integral, but this time in polar form, is going to be the double integral of f of, well, remember x is going to be equal to r cosine theta, so we have f of r cosine theta comma y, which is r sine of theta, times r times dr times d theta. And so the inside integral is going to have the r bounds from a to b. So we have from a to b, and the outer integral, since the outside has d theta, and the outer integral is going to have the theta bounds from alpha to beta. So you should be pretty familiar with these three formulas because we use these in polar form and also when converting into cylindrical coordinates. So two things to keep in mind here: the inside integral is always going to have the r bounds, and the outer integral will have the theta bounds. And then remember that whenever we're trying to find the double integral in polar form, we always have to multiply by that extra r variable. Now this might look a little bit confusing at first, but all we're doing here is taking the function that is given to us and basically using these three formulas to turn it into polar form. So for this first problem, let's go ahead and sketch the region whose area is given by the integral and then evaluate the integral. So for number one, we have the double integral from pi to 2 pi and from 4 to 7 of r dr d theta. So if we were to go ahead and sketch this region, realize that the outer integral once again is the bounds in terms of theta. So we can say that theta goes from pi to 2 pi. And then the inner integral is the bounds in terms of the r, or the radius. So the r values go from 4 to 7. So whenever you see just r by itself in polar form, that's basically describing a circle. So if I were to go ahead and draw a circle here, the radius once again ranges from 4 to 7. So let's just draw an inner circle here, and the radius of the inner circle is 4, and the radius of the outer circle will be 7. So that tells us that the radius ranges from 4 to 7, so it's in between these two circles. Now notice that theta values are from pi to 2 pi. Now pi is 180 degrees, 2 pi is 360. So we're really starting here at 180 degrees and then going all the way to 360. So the area we're looking for, or the area of the shaded region, is basically this area right here. So now let's go ahead and evaluate this integral. So if I write the inside integral here, we have the integral from 4 to 7 of just r dr, and so the integral of r is just r squared over 2 if we are integrating with respect to r. And if I evaluate it from 4 to 7, 7 squared is 49 over 2, and then minus, when I plug in 4 for r, we'll get 16 over 2. So then 49 minus 16 is 33 over 2. So now I can go ahead and say the outer integral from pi to 2 pi of 33 over 2 d theta. So now we're going to integrate with respect to theta. So the integral of 33 over 2, since that's just a constant, is going to be 33 over 2 times theta. And so let's go ahead and integrate from pi to 2 pi. And so when I evaluate, we get 33 over 2 times, when I plug in 2 pi for theta, we'll get 2 pi, minus when I plug in pi for theta, we just get pi. 2 pi minus pi is just pi, and then pi times 33 over 2 will give us 33 pi over 2 as the final answer. So for these next set of problems, let's go ahead and evaluate the integral by changing to polar coordinates. So for number one, we have the double integral of x times y dA described by region D, where D is the disk with center of the origin and has a radius of 3. So if we were to draw out this region here, if we're talking about a disk, this is basically just a circle in the xy plane. And so the center is at the origin, so at 0, 0, and the radius is at 3. So we can easily say that the radius goes from the values of 0 and to 3. So that is going to be the r bounds. Now for theta, realize that this is a complete circle. So we're basically going a full 360 degrees or a full 2 pi radians. So this tells us that theta is going to go from 0 to 2 pi. So if we go ahead and rewrite the integral, we can say the double integral. Now the theta bounds are going to be on the outside integral. So we can say from 0 to 2 pi. And the r bounds are always going to be on the inner integral. So that is going to be from 0 to 3. Now remember, we also need to change the function so that it is in polar form as well. So remember that x equals r cosine theta. So I can simply just replace it with r cosine theta times y, which is also equal to r sine of theta. And remember, in polar form, we always need to multiply by that extra r variable. So we multiply by r, and then we can go ahead and multiply it by dr and d theta. So if I were to go ahead and simplify this a little bit, I'll just go ahead and multiply r cosine and r sine and multiply r as well. So we get r squared cosine theta times sine of theta. Then we have another r, so if we multiply that by that, we then get r cubed times cosine theta times sine of theta. So now I can go ahead and rewrite the integral as the double integral, the outer one from 0 to 2 pi, once again that's our theta bounds, and the inner one from 0 to 3, those are our r bounds for the radius, of r cubed times cosine theta times sine of theta, and then we have dr d theta. So if I go ahead and rewrite the inside integral first, we have for integral from 0 to 3 of r cubed cosine theta times sine of theta dr. And so we're going to integrate with respect to r. So cosine theta, sine and theta are just constants. So we can take that outside of the integral and say cosine of theta times sine of theta times the integral from 0 to 3 of just r cubed dr. So the integral of r cubed is r to the 4th over 4. And if I evaluate that from 0 to 3, so when I plug in 3, we will get r to the 4th, so 3 to the 4th is 81, so 81 over 4, minus, when I plug in 0, we get 0 over 4. That will just cancel. So we're left with 81 over 4. Don't forget we did have that constant on the outside of cosine theta, sine of theta. So we get 81 over 4 times cosine theta, sine of theta. So now let's go ahead and put that under the outer integral here from 0 to 2 pi. Now remember, 81 over 4 is a constant, so I can take that outside of the integral. So from 0 to 2 pi of cosine theta, sine theta, this time we're going to integrate with respect to theta. So this one's just a simple u substitution problem. If I set u equal to sine of theta, I'll be able to cancel out the cosine theta. So if u equals sine of theta, then du, or the derivative of sine of theta, is cosine theta d theta. So then d theta is going to equal du over cosine theta. Now when I go ahead and plug that back into the integral, we'll get 81 over 4 times the integral from 0 to 2 pi. Remember, those are our theta bounds, of cosine theta times u, because I made u equal to sine of theta, times d theta, which is equal to du over cosine theta. Notice the cosine thetas will cancel, and if I'll just write it up here, we're left with 81 over 4 times the integral from 0 to 2 pi of just u times du. And so the integral of u is just, we get 81 over 4 times the integral of u, so then u squared over 2. If I go ahead and multiply 4 and 2, we get 8. So we get 81 over 8 times u squared. And remember, we made u equal to sine of theta, so I can go ahead and plug that back in. So we get sine squared of theta. Let's go ahead and evaluate that from 0 to 2 pi. So when I plug in 2 pi, 81 over 8 times sine of 2 pi is basically 0. 0 squared is 0. Minus sine of 0 is also 0. 0 squared is 0. So 0 minus 0 is 0. And 0 times the 81 over 8 is also 0. So our final answer is actually 0. So for number 2, let's go ahead and find the double integral of cosine of x squared plus y squared dA, described by region R, where R is the region that lies above the x-axis and within the circle x squared plus y squared equals 9. So if I were to go ahead and sketch the region here, x squared plus y squared equals 9 is just the equation of a circle with a center at the origin 0, 0 and a radius of 3. So it looks something like this. Now R is going to be the region that lies above the x-axis. So it's going to be above the x-axis but within the circle. So we're basically looking at this shaded region here. And so these are the bounds of integration. Now let's go ahead and first look at R. Now the values of R are going to obviously range from 0. If I were to draw this out, it's going to range from 0 all the way to 3. So R is going to be from 0 to 3. And notice we're only covering, the region is only a half circle. So we're basically starting at 0 radians and going to not 2 pi, but only pi radians. So that means theta ranges from 0 to pi. So rewriting the double integral, we'll get the double integral. Now the outer integral is going to be in terms of theta, so 0 to pi, and the inner integral is going to be in terms of r, so from 0 to 3. Now we have cosine of x squared plus y squared. If we're going to turn this into polar form, remember that x squared plus y squared equals r squared. So I can basically say cosine of r squared. Now don't forget, when we convert into polar form in double integrals, we always have to multiply by the extra r, and then we have dr d theta. So rewriting the integral, we get the double integral, the outer one from 0 to pi, once again the inner one from 0 to 3, of r times cosine of r squared times dr d theta. So rewriting the inner integral, realize that since we have an r squared and an r, this is just a simple u substitution problem. So r times cosine of r squared dr. If I make u equal to r squared, then du, or the derivative of r squared, is 2r dr. So then dr is going to equal du over 2r. When I go ahead and substitute that back into the integral, we get the integral from 0 to 3 of r times cosine of r squared, which I set it equal to u. So cosine of u times dr, which is equal to du over 2r. Notice the r's will cancel. 1/2 can come outside the integral because it's a constant. So we'll get 1/2 times the integral from 0 to 3 of cosine of u du. Now the integral of cosine is just sine of u, so we get 1/2 sine of u. Remember we made u equal to r squared, so I can go ahead and plug that back in. So we get 1/2 times sine of r squared. So now let's go ahead and evaluate it from the bounds of 0 to 3. Plug both of those in for r. So then we get 1/2 times sine of r squared, so we get sine of 9 minus sine of 0 squared, which is sine of 0. Sine of 0 is obviously 0. So that will cancel. And so we're left with 1/2 times sine of 9. Now we can go ahead and say the integral from 0 to pi. Now it's the outside integral, since we've already found the inner integral, of half sine of 9 d theta. We're going to integrate with respect to theta now. Realize that the entire thing, half times sine of 9, is all a constant. So when I integrate with respect to theta, we just get half times sine of 9 times theta, since the entire half sine of 9 is a constant itself. So we're going to evaluate from 0 to pi. Those are going to be the theta bounds. I'm going to combine sine of 9 times 1/2 and rewrite it as sine of 9 over 2. So we get sine of 9 over 2 times, when I plug in pi for theta, we'll get pi, minus when I plug in 0. So we're just basically just left with pi over 2 times sine of 9 as the final answer. So now for number 3, we have the double integral of e to the negative x squared minus y squared dA, where d is the region bounded by the semicircle x equals the square root of 4 minus y squared and the y-axis. Now if I were to start by drawing out this region here, now the equation, let's say we have, instead of x equals, let's say we have y equals the square root of 4 minus x squared. So if I were to go ahead and draw out y equals the square root of 4 minus x squared, in this case this will be a semicircle in the positive y-axis. And it's going to have a radius of 2. Now instead of y equals, we have x equals square root of 4 minus y squared. So this will be a semicircle in the positive x-axis, and it'll have a radius of 2 as well. Now it's telling us that D is the region bounded by the semicircle and the y-axis. So we're basically looking at this entire region here. Now the bounds for R, the radius, are going to go from 0, obviously, to 2, because the radius is 2, so that is going to be the R bounds. Now the bounds for theta, realize that it's starting at negative pi over 2, or negative 90 degrees, and then going all the way to positive pi over 2, or positive 90 degrees. So we can say that it's going from negative pi over 2 to positive pi over 2. So rewriting the double integral, we get the double integral. Now the theta bounds are on the outside, so from negative pi over 2 to positive pi over 2. The R bounds are on the inside from 0 to 2 of e raised to the power of negative x squared minus y squared. Now if I were to factor out the negative, we get negative 1 times x squared plus y squared. Remember, x squared plus y squared is equal to r squared, so we basically get negative r squared. Don't forget, we do have to multiply by the variable r, and then we have dr d theta. So rewriting the inner integral, we have the integral from 0 to 2 of, I'm going to put r first, so r times e to the negative r squared dr. And so once again, this is also a u substitution problem. So if I said u equal to negative r squared, du, or the derivative, will be negative 2r dr. So then dr, if I isolate it, will be du over negative 2r. So if I plug that back into the integral, we get the integral from 0 to 2 of r times e to the u, because I made u equal to negative r squared, times dr, which is equal to du over negative 2r. The r's will cancel. Negative 1/2 can come outside the integral as a constant. So we get negative 1/2 times the integral from 0 to 2 of e to the u du. Now the integral of e to the u is e to the u, so we have negative 1/2 e to the u, which is equal to negative r squared, so I can plug that back in. And then we can go ahead and evaluate it from 0 to 2. Now if I go ahead and plug in 2, we'll get negative 1/2 times e to the 2 squared, which is 4 times negative 1, so negative 4. And then minus, when I plug in 0, e to the 0 is just 1. If I go ahead and distribute the negative, we will get 1/2 times 1 minus e to the negative 4. And so now let's go ahead and evaluate the outer integral from negative pi over 2 to positive pi over 2 of 1/2 times 1 minus e to the negative 4 d theta. Now this entire thing is a constant, so when we integrate this with respect to theta, the integral is just going to be 1 minus e to the negative 4. I'm just going to rewrite it as that over 2 times theta. And then so when we evaluate it from negative pi over 2 to positive pi over 2, we'll then get, I'll actually write it down here, we'll get 1 minus e to the negative 4 over 2 times, when I plug in pi over 2 for theta, we get pi over 2, minus a negative pi over 2, so then plus pi over 2. Pi over 2 plus pi over 2 is 2 pi over 2, or pi. So we're left with pi over 2 times 1 minus e to the negative 4. That's the final answer. Now for this next problem, we're going to learn how to use a double integral to find the area of a polar region. Now from Calculus 2, the formula for the area under a polar curve is area equals just 1/2 times the integral from alpha to beta of r squared d theta. And so once again, alpha and beta are just the bounds in terms of theta. Now how can we use a double integral to find the area under polar curves? Well, let's say we are given a polar equation, so r equals some function h in terms of theta. Then we can use the formula where area equals the double integral. Now the first one is just going to be from alpha to beta, the outer integral, because that's just in terms of theta. And then the r bounds are going to be from 0 to the given equation, h of theta. So some function in terms of theta of just r times dr d theta. And the good thing is when you integrate the inside portion, you will get right back to this formula. So let's go ahead and use a double integral to find the area of the region. And for number 1, we have one loop of the rows, r equals cosine of 3 theta. Now if I were to go ahead and graph r equals cosine of 3 theta, this polar equation, we get something like this. We get a rose with 3 petals. And notice we just want to find one loop of the rows. So let's go ahead and just shade in this loop here. And so once again, if I were to rewrite the double integral formula to find the area, the outer integral is just going to be in terms of theta, so the angle from alpha to beta. The inner integral is going to be from 0 to the given function, cosine of 3 theta of just r and then times dr d theta. Now how can we find alpha and beta? Well, if I use a graphing calculator here, we start at this point. So this is at theta equals 0. Now if we go all the way here to the origin, we first meet there at theta equals pi over 6. So if I instead go backwards negative pi over 6, we also go back to the origin. So theta equals negative pi over 6. So basically I can say that we want to go from negative pi over 6 all the way to pi over 6. So I can say that's the range of theta values. From negative pi over 6 to pi over 6. So I can go ahead and rewrite the double integral. The outer one is going to be, once again, from negative pi over 6 to pi over 6 to just find one loop of the rows. And then we have from 0 to cosine of 3 theta. We have r times dr d theta. And so now we can go ahead and evaluate. So if I write down the inner integral from 0 to cosine of 3 theta of just r dr, the integral of r is r squared over 2. If I go ahead and evaluate that from 0 to the function cosine of 3 theta, we get cosine squared of 3 theta over 2 minus, when I plug in 0, we get 0 squared, which is 0, over 2 is also 0. So we're just left with cosine squared of 3 theta over 2. So now we can go ahead and integrate this from negative pi over 6 to positive pi over 6 with respect to theta. Now with this, I can also put 1/2 outside of the integral since it's a constant. We have 1/2 times the integral of cosine squared of 3 theta. Now we can't necessarily integrate this by hand, so what we can do is use a trig identity here, where cosine squared of x, or in this case we have theta, so let's say cosine squared of theta is going to equal 1 plus cosine of 2 theta over 2, or 1/2 times 1 plus cosine 2 theta. But realize instead we have cosine squared of 3 theta, not just theta. So cosine squared of 3 theta is just going to be equal to 1 plus cosine of 3 times 2. This time we have 6 theta over 2. And so we can go ahead and replace these two. So then we get the 1/2 times the integral from negative pi over 6 to positive pi over 6 of 1 plus cosine of 6 theta. Now over 2, remember that's 1/2 as a constant, so I can bring that outside. So then 1/2 times 1/2 will give me 1/4. So we get 1/4 times the integral of 1 plus cosine 6 theta, and we're going to integrate with respect to theta. Now the integral of 1 is just theta. We get 1/4 times theta plus the integral of cosine of 6 theta is 1 over 6 sine of 6 theta. Let's go ahead and evaluate that from negative pi over 6 to positive pi over 6. So when I plug in pi over 6 first, we'll get 1/4 times pi over 6 plus 1 over 6 times sine of 6 times pi over 6. Now 6 times pi over 6 is just pi, sine of pi is 0, so we'll just get 0. Minus, when I plug in negative pi over 6, we'll get negative pi over 6 plus, once again, sine of negative pi, or negative 6, or 6 times negative pi over 6 is negative pi. Sine of negative pi is also 0, so we'll still get 0 here. Now the zeros will cancel. Pi over 6 minus a negative pi over 6 will be positive 2 pi over 6, which is pi over 3. So we get 1/4 times pi over 3, which will give us the final answer of pi over 12. So now let's go ahead and use polar coordinates to find the volume of the given solid. So for number 1, we need this volume of the solid that's under the paraboloid z equals x squared plus y squared, and above the disk x squared plus y squared is less than or equal to 9. So let's go ahead and first start by drawing the disk. Now we have x squared plus y squared is less than or equal to 9, but I'm going to first start by drawing out x squared plus y squared is equal to 9. So that's obviously just a circle with a radius of 3. But it's telling us that x squared plus y squared is less than or equal to 9. So we're basically looking for the shaded region that is everywhere inside of the circle. So So if we were to find the r bounds and the theta bounds here, we know the radius obviously goes from 0 to 3, so that is going to be the r bounds. So from 0 to 3. And for theta, obviously this is a full circle, so we're starting at 0 radians and going all the way to 2 pi radians. So the theta is going to go from 0 to 2 pi. So now remember, a double integral of some multivariable function is going to give the volume of a solid under that function. And so since we're trying to find the volume under the paraboloid, given that x squared plus y squared is a multivariable function, we can basically put it in this format. So if I rewrite it, we have the double integral of the multivariable function, x squared plus y squared. So now the only thing left to do is to change it into polar coordinates. So once again, x squared plus y squared equals r squared. So I can rewrite it as the double integral of r squared. Don't forget, we need to multiply by that extra variable r when we use double integrals to find volume. And then we have dr d theta. Now once again, we've already found our r and theta bounds. So r goes from 0 to 3, that's going to be on the inside integral. And the outside integral, theta bounds are from 0 to 2 pi. So obviously r squared times r is r cubed. So if we go ahead and integrate r cubed, we'll just get r to the 4th over 4. Let's go ahead and evaluate that from 0 to 3. So we get 3 to the 4th, which is 81, so 81 over 4, minus 0 to the 4th, which is 0, over 4, which is also 0. So we get 81 over 4. So if I rewrite that, let's go ahead and now integrate the outer portion here, 0 to 2 pi. And so the integral from 0 to 2 pi of 81 over 4, with respect to theta this time, obviously this is a constant, so the integral is just 81 over 4 theta. Let's go ahead and integrate or evaluate from 0 to 2 pi. So then we'll get 81 over 4 times, when I plug in 2 pi for theta, we'll get 2 pi, minus when I plug in 0 for theta, we get 0. So that cancels. And so we're left with 162 pi over 4. And so that can simplify to 81 pi over 2. And that's the final answer.